In this video, we're going to talk about the direction angle of a vector and how to find direction angles. So the definition for direction angle is that it's the angle formed by the vector in standard position and the positive x-axis. So this is going to look very much like what we've been doing in trig for a long time, just in a different context. So suppose we have a vector v and it's given, and I'm going to give it to you first in ij form, just so we can kind of review and refresh our memory on what that is. So if v is the vector negative 2i minus 5j, we know that that means the same thing as the vector v negative 2, negative 5 in component form. And you're welcome to convert it if that feels more comfortable. Now I'm going to draw a picture of this. So here's our xy axis, and we have negative 2 in the x and a negative 5 in the y. And so our vector is going to come from the origin to that point, negative 2, negative 5. So there is our vector v given in standard position. So what we want is what's known as its direction angle. And so that angle theta, which goes from the positive x-axis to that vector, is the direction angle. Generally, we try to make that be a positive angle, but you would certainly be understood if you chose your angle to go in the negative direction. So that's not exclusive. So what we can see is from work we have done earlier that if we look at our reference triangle, then we have a negative 2 and a negative 5 for the sides of that. This reference angle here, when we allow for the negatives, is going to be the same as that green angle that we've drawn from the positive x-axis. So we can see that the tangent of our angle theta is opposite over the adjacent, and because of the two negative signs, that means our tangent theta is 5/2. And so we can find the inverse tangent of 5/2 to get our angle theta. Sometimes this will be given in degrees, sometimes in radians. Most of the time in our examples in this chapter, we're going to be in degrees. So you want to put your calculator in degree mode, and if you do that, I believe you should get 68.2 degrees. Now we have to interpret here, so we can't just blindly follow what our calculator has given us. We can see from the components of this vector and from our graph that this vector is actually down here in quadrant 3. 68.2 degrees would be a quadrant 1 vector. And so what we've really gotten here with our 68.2 degrees is our reference angle. So what we have to do is make that adjustment and say, well, to put that into quadrant 3, we're going to have to add 180 degrees to that. And so you have to, in general, interpret and compute where your actual reference angle is going to be, and not just go with the inverse tangent. Oops, I should have put an inverse tangent there of 5/2. Okay, let's do another example. So I'm going to go to a new screen, and let's find the direction angle for our vector w this time, and w is going to be in component form negative 3, 2. So if you want, you can pause your video for a minute, see if you can work it, and then see if we end up getting, hopefully, the same thing. So I'm going to go to negative 3, 2. I like to draw that vector w and see that it's actually going to be here in quadrant 2. So there is our direction angle, and that direction angle is going to be the inverse tangent of the y value over the x value. And so if we do that, on our calculator, make sure you're in degree mode. I believe you're going to get 33.7, it'll actually be a negative 33.7 degrees. Remember, our calculator is telling us, is programmed to, when we take an inverse tangent of a negative, it's trying to give us a quadrant 4 angle. And so what we have found is that this angle is the negative 33.7. So what we actually want for our angle is for this to be the reference angle of 33.7, which is going to make our quadrant 2 angle be 180 minus 33.7, which is, I believe, 147.3 degrees. So that is going to be our direction angle for that vector. So we want to also talk about what is called resolving a vector. So when you hear the words resolve the vector, what that is going to mean is that we'll be given a magnitude and direction angle, and what we want to do is to be able to write the vector in its component form, either by finding with the ij form the ai plus bj, or we could write it in component form as a comma b. So to see where this comes from, this is just our trigonometry. So I'm going to draw a vector. I'm just going to put it into quadrant 1 to make it a little simpler, but it doesn't matter which quadrant we're in. This is the A and the B that we are looking for. We will be given the magnitude, which I'm going to call V. So we're going to resolve the vector, which means we want to find, so I'm going to say given the magnitude of the vector and its direction angle. So there's our magnitude and direction angle theta. So here is our theta. So we can see from our trigonometry knowledge that if we're trying to find A, that the cosine of theta is going to be A over the hypotenuse, which is the magnitude of that vector. And that tells us then that A is going to be the magnitude of the vector times the cosine of the direction angle. Similarly, we're going to get sine theta is going to be B over the hypotenuse, the opposite over the hypotenuse, and that's going to tell us that to find B, we're going to get the magnitude of the vector times the sine of theta. So what we're going to find is our vector V in general is going to be the magnitude of V times the cosine of theta times the magnitude, and comma, magnitude of V times the sine of theta. So this is what we're going to do to resolve the vector into its components. Now, when you can see it in this form in general, it's kind of nice to see then that a unit vector is going to look somewhat familiar, I think. Remember, a unit vector in the direction of V, we said was the vector V divided by its magnitude. So that means our unit vector in the direction of V, if we take this vector V and we divide by the magnitude, it turns out to be just the cosine of the direction angle, comma, the sine of the direction angle. And you might note that the magnitude of this direction vector would be just the square root of sine squared theta plus cosine squared theta, which we know is going to be 1. So that's how we know it's going to be a length of 1. All right, well, let's see how this is done in practice. Let's do an example. So let's find the components. I'm going to find the components. of vector W with direction angle theta equal to 150 degrees and magnitude of 6. So that's going to be part A. And then secondly, we're going to find a unit vector in the direction of W. A unit vector in the direction of W. So first of all, what we're going to do for part A is we're going to say that this vector W, according to what we just talked about, is going to be the magnitude of W times the cosine of theta, comma, the magnitude of W times the sine of theta. And so that is going to look like 6, which is the magnitude, times the cosine of 150 degrees, comma, 6 times the sine of 150 degrees. Now these are values that we know, I hope. So 150 degrees, remember, is going to give you a reference angle of 30. Cosine of 30 is square root of 3 over 2, but 150 is in quadrant 2, which is going to make that be a negative. And the sine of 150, has a reference angle also of 30, and that's going to be 1/2. And in quadrant 2, sine is still positive. So our vector W, when we resolve the vector into its components, it's going to look like -3 square root of 3, comma 3. So there is our answer to part A. For part B, we know that the unit vector, this is my Mr. Street made-up notation, but who can argue with how good communication it is? A unit vector U in the direction of V is going to be just the cosine of that direction angle, comma, the sine of that direction angle. And so that is going to be a negative square root of 3 over 2, comma, 1/2. Okay? Very good. Let's stop there, and I'm going to make another video with some examples.